others characteristic, the important characteristic that we will elaborate after this. Okay. So next, we go to the basic structure. The basic structure. For here, I will give the example of single mode fiber. It is contain three layers, which is buffer and coating, and then the cladding, and then also how can I? Oh, it's okay. Okay, then we got the core. So a core is the inner part where the light is propagated, while the cladding is outer. The outer part is protect the light in the core, and then it can transmit smoothly. And we can see here the cross section. The outer diameter standard fiber optic for telecommunication is a 125 micrometer, and the core normally the standard size of the core is normally a 9 micrometer. Okay, as we can see here, the block diagram for the block, we can see the block diagram here is contain a 3 part, which is source and the elements, sensing element, and then the detector. The sensing element is our sensing head, which is this part is very sensitive to the surrounding. Okay, the sensing element is the part that we designed to be highly responsive to the target measurement parameters. And then the source is normally we use a laser source, and the detector we use interrogator and also optical spectrum analyzer, OSA. In the term, another term that I would like to define here is optical fiber sensor. The term is referred to the device that use fiber optic as a sensing element, or a device that use fiber for transmit the sensor signal. Okay. Next is a type of fiber optic. The basic, normally we use a single mode fiber and multi-mode fiber for fiber optic sensor, but there are many specialties fiber out there, such as a porous fiber, multi-core fiber, double clad fiber, few mode fiber, and also photonic crystal fiber. For my PhD, I use a double clad fiber to fabricate my sensor. Okay. As I said before, the needs of fiber optic sensor is come from the advantages of the fiber optic itself, because the fiber optic is lightweight, small and compact in size, easy to multiplex, immune toward electromagnetic interference, flexible and low cost. This is a very important factor to contribute to Industry 4.0, because we want to more sustainable. We want to improve the performance of our fiber sensor, and then we want low cost. Okay, the performance we can play around with the performance of fiber optic sensor by the fabrication technique, digital signal processing, the sensor material itself, and the specialist optical fiber that we use. And the technique that we can use is we can apply to our fabrication is tapering, etching, laser micromatching, grating writing such as fiber grating, chemical decomposition. And the parameter that can we focus on by using fiber optic sensor is temperature, refractive index, strain, pressure, curvature, displacement, acoustic, and also vibration, and humidity. Is lot we can achieve for fiber optic as a sensor. Okay, we can classify the fiber optic sensor by 4. The first one in the term of modulation, in which how the optical signal properties are changed because of the perturbation. This include the intensity, wavelength, phase, and polarization. And the second classification in the term of principle, the main principle used in sensing, such as interferometry, grating, scattering, spectroscopy. Actually, there are few other principles that are not listed here, but main focus today is interferometry. Yeah, because I used this one for my PhD. Okay, then in the term of spatial scope, whether the sensor is deployed as a point sensor, which for a localized measurement, or is term of quasi-static. The multiple point sensor is arranged to measure a several point. And then for distributed, lastly, the application, we can go to the physical, chemical, and also biological. Okay, fiber optic sensor. The interferometric sensor, which is have strip 4, which is Fibre, Mach-Zehnder, and also Mach-Zehnder interferometer, and Michelson, and also Siti. For the grating based sensor, which is a fiber break grating, there is a long period grating. It's just the same, but with the long period one, the cheap fiber break grating. Sorry for the misspelling that. Cheap fiber break grating. And for the distributed sensor, there is 3, which is Raman scattering, Rayleigh scattering, and Brilliant scattering. But today we focus on interferometric sensor, and I will discuss more about that. Okay, for the interferometric sensor, we have 4, right? So basically, normally for now, the today's technology, researchers more focus on the Michelson and the Mach-Zehnder, because it's easy to fabricate and more flexible to it, what we want to do. And then it's also give high sensitivity. As we can see, the Michelson, we only need to use one coupler, which is to separate the light from the laser. When the light from the laser come to the coupler, and then the light will split and then couple back there to the detector. And also same with the MZI there. The first coupler is for the splitting, and then the second coupler is recombine back the light from the sensing arm and refer arm to the detector. Okay, the Fibre is like just the same, but the is different. Is have a double mirror here, the partial mirror, so that it can be reflect back the light. Okay. Is it okay? My presentation today, is it okay or a little bit fast? Nadia?
I think it's okay for me.
Okay. Okay. And next, the technique how we want to use MZI, or I give example MZI or MI. Okay, for this, how we want to fabricate the fiber. Okay, for this one, the core size matching of MMF, we use MMF as a coupler. Before this, I show you. For MZI, we need a 2 coupler. So here MZI act as a coupler where the light travel through the SMF and then split to MMF, and then couple back at the second MMF and to the SMF. Okay, for the second is core size mismatch of thin core fiber. We use a thin core fiber to to have a different different size diameter of the core. The single mode fiber have a larger core, and then the light can split through the after they face a thin core fiber, and then recouple back at the end of thin core fiber. The what the principle are the same, but we just modify our fiber. Okay, so the third is small lateral offset. We just do a small offset there to give to dislike the core so that the light can travel through the cladding. Okay, for the large lateral offset, we want the light travel to the surrounding and then couple back, so that here we can do such as RI parameter, and also for the taper fiber, it's just the same. We just use for the taper fiber, we can use a splicing machine to create the taper fiber. But maybe if we use a splicing machine, we cannot do a lot of tapering. Maybe if we want to use we want to do a multiple point of tapering, maybe we can use a femtosecond laser. It's more uniform. Okay. Then the bubble fiber is much different with a taper fiber, but the concept is there because for the taper fiber is just like that, right? So for the bubble fiber, the fiber must compress, and then it can build the bubble fiber. Okay. This one I think also we can use the splice machine, and the lastly is open cavity fiber using the femtosecond laser. This one we just cut the fiber in the square. Okay. As I said before, these are all the parameters that we can apply for by using we can test by using a fiber optic sensor, which is acoustic, temperature, bending, curvature, strain, refractive index, water level, pressure, humidity, and much more, I think. Okay. So then we move to the literature review. It's from this one. I give the example, the Michelson interferometer for simultaneous temperature and refractive index sensing. Okay, as we can see here, they use a thin core fiber, as I showed before, and then thin core fiber, and then the technique that they use is Michelson interferometer. The length is very, very small. The sensor head is very small. It's approximately just 2 mm. And then this one is they use a thin core fiber. This one is thin. It's tapered fiber. Tapered fiber, and then they combine with a Fresnel. Okay, Fresnel is normally for a refractive index. As you can see here. For this they use offset single mode, and also in the single mode they fabricate the fiber embedding inside so that they can sense temperature. Okay, for the offset, because they do the offset, so they can send the refractive index also. Okay, for 2017, this is my PhD. A part of my PhD, I use a double clad fiber, and the length is 18.5. Okay, I do a several length, but this one is the best result I get. I use a DCF. The whole section of DCF is for temperature, and the tip of DCF for refractive index. I use a Fresnel reflection, and Okay, they also use photonic crystal fiber. Okay, next. This is an example for refractive index and discrete liquid level. Okay, for this one, they use knockoff fiber. Knockoff fiber, and the length is 45. And the technique that they use is Nicholson interferometer. And then they also we can also use double hole elliptical core for this to sense the reflective index and also liquid level. But sometimes they for my research is in 2021, I use for just discrete water level. It's not the whole fiber can sense the what liquid level. I just do a point sensor. Okay, for this one they use in 2020 they use a local fiber, and also at the tip for refractive index they use SMF or argon film at the tip. Okay, so for the Alexander interferometer, displacement and curvature, this one is not for my case. I used to sense to test two displacement range and also curvature, which is there's before this they just use for displacement, but for the curvature high curvature they don't use this for both. They just for displacement and then another fiber for the curvature. They don't use this one for multi-parameter. So it's just a new technology. We can use also we can use DCF for displacement and also curvature. Okay, as we can see here also in 2019 they also use a double clad fiber and a ceramic tube. But the technique they use is Fibre. Okay, here just they use in 2015 they device SMF with peanut section and also photonic crystal fiber, and then couple back to the single mode fiber. Okay. Okay, this is a design that I use for my PhD, which is I use a three component of fiber, this type of fiber optic sensor, which is single mode fiber, multi-mode fiber, and double clad fiber. These three type can give me can provide me to get a multi-parameter sensor, which is I do for temperature, refractive index, discrete water level, and also displacement and curvature. But I play around with the, as you can see, I play around with the length and also the structure of the fiber optic. What I create is here is a commonality, because I can use the same type of fiber for different type of parameter. So for the first design, I use single mode fiber, multi-mode fiber, and double clad fiber, and then at the tip. For this one, I use a reflection mode. Yeah, I can send a temperature and reflective index. And at the second, I put at the middle of my first design, I put SMF, so that here I can sense the discrete liquid level sensing. And then the third one, I just elongate the DCF, and then I do for displacement and curvature sensing. So here we can achieve that we can play around with the structure, and then we can achieve the different tests, different temperature, different parameter. Okay. So how first, also how I know whether my fiber is, my design is working. So I do a numerical simulation. Yeah, for this one, I want to know whether if I do the etching at the middle, whether the light will travel to the surrounding or not. So I do the numerical simulation by using a beam probe. Okay. So, okay, next we move to the methodology, the experimental setup, where which is contain temperature, refractive index, water level, and also curvature. So this temperature, we use ASE as a laser source, and then for the reference, I use a digital thermometer, and then I put the sensor inside the oven, and then the detector is an optical spectral analyzer, and then we just use a lab view to see the data, to receive the data at the computer. So for the refractive index is also the same. Yeah, just I use a liquid RI liquid to vary the RI index. Okay, this the laboratory setup. The setup is all in Faculty of Engineering UTM. Okay, this is how I do the water level, because it's discrete, right? So I just put the a drop of liquid level at one point at one time. Okay, so this is, yeah, we cannot see clearly, but it's there. Okay, the bending, how sometimes we must think out of the box, because in my cases, the bending setup is I try to figure out myself, so that I use a plastic ruler at the okay, you can see here at the stage, so that yeah, we must be creative, because sometimes it's not in our lab is not have enough equipment, so that if we want to do that, so we must be creative. Okay, next is how I use for high curvature. Okay, I just take a block of metal, so that my fiber is still there, it's not moving. Okay, this is sorry, yeah, this for the application, we can use the multi-parameter sensor, such as for the temperature and refractive index in food inspection, oil and gas, and also chemical for the liquid level, it may be in chemical storage, and then for aerospace also, and for the wearable medical health also we can do, as I said before, the structural health monitoring and soft robotic. And then, okay, for the conclusion, why I want to focus on, before this, I want to focus on why commonality, because in Industry 4.0, we want to reduce waste, sustainable, we want to lower the cost. So when we use the same type of fiber for different type of parameter, so that we can contribute to it nowadays technology, so then we can be more efficient and as well as low cost. And then why I want to do, why we must to do multi-parameter sensing, because we can improve the productivity and we can control the variation of the component itself. So, and then lastly, why fiber optic? Because the advantages of fiber optic, because it's small in size, and then immune to an electromagnet, flexible, highly sensitive, and then because and with with that advantages, the sensing capability is very, very high. Okay. Yeah, this is my publication. So I just published for this year. I just published the books chapter. Okay. So that's all for me. Thank you.
Thank you so much, Dr. Musliha. That was a very engaging talk. I think this is it's been a while that we have someone talking about fiber sensors in general, because we have been talking about materials a lot on our platform. So we have several questions here. So the first one is from Dr. Yo. Is the sensing region at the tip of the fiber or the surrounding of the concatenated fiber?
Yeah, it depends on the type of fiber that we use. So as I said before, if we want to, as I use a double clad fiber, right? So double clad fiber is confined. The light is confined inside the fiber. So when we want to use the tip of fiber, we just clip straight, and then the light will travel at the surrounding, and then couple and then goes back to the core. Yeah.
Is there a diagram that you can show us where the light propagates?
Okay.
Yeah. So how do you ensure that the light goes back into the core? Is there like a special setup for that?
Okay. No, it's not special setup. Okay, fine.
Or is it not able? You can't go back.
Yeah. Okay, it's like this one. So laser pointer, okay. So can see my laser pointer? Yeah? No?
Laser pointer, not yet. But the slide, yes.
Okay, the slide, yes. Laser pointer. Okay, there. So for this one is I use for a temperature and refractive index, right? So at the tip of fiber, we can sense the refractive index because the light is travel. Here we use a Fresnel reflection. Fresnel reflection. So that the light will travel to the surrounding and then goes back into the fiber. So just like this one, when we want to sense the parameter such as a refractive index, right? So outside of our sensor, so we must do some modification. So, such as for this one, we use a fiber so that the light can travel to the surrounding and then couple back.
What about when you mentioned the whole DCF was the sensor region itself? You mentioned earlier.
Yeah, for that one, the whole DCF is for temperature because when we want to do a simultaneous parameters such as temperature and refractive index. So how we can divide whether this peak is for temperature, and also how we want to reduce the cross sensitivity, right? So when we do the temperature, we get the peak, and then for when we do the with the peak at we get the spectrum at our OSA, so that for the refractive index also we get the peak. So we just make sure that our peak is not overlap. so that when when we test for temperature, the peak for refractive index is not have a much significant change in terms of intensity and also wavelength. Yeah.
So from my understanding of your explanation, so the different parameters will have their own peaks at different wavelengths and they will shift according to the variation.
Yeah.
Okay.
Yeah.
Okay, so we have more questions coming in. So how do you fabricate on small segments of DCF, MMF fiber using what type of fusion splicer machine? And are there any special settings required? This question was from Shafika Rodzi. Thank you.
Yeah, it don't have any special, but you must have a lot of, okay. Most welcome, Dr. Yo. We have a lot try and error for the small section. Of course, we must use microscope, and I also use a normal splicing machine. Yeah, for the fabrication, I just use a normal splicing machine. But sometimes you must use manual setup, not in auto setup. Yeah. I hope I answered your question, Safika.
Do you have like a specific brand of fusion splicer that you always use to fabricate your sensors?
I forget, but I think it's all fiber optic labs have, but you can use. But before this, I use the old splicing machine is okay, is work. But sometimes the splicing machine don't have manual modes. But you can try. Yeah, you can try and error.
What about? Can I ask about the splicing points? Are the splicing points going to be sensitive to your the environment that you're testing in?
Yeah, if we do a splicing, the splicing point is we have a loss, but still we can get, but it's not sensitive to the parameter that we want to test. Yeah, it's not have a big significant issues there.
So we have another question. Thank you, Dr. Musliha. We have another question from Intan Fatima Sasila. Thank you. Why do you choose interferometer sensor instead of FPG and distributed sensor?
Yeah, okay. For that one, I want to use this one because I want to emphasize the functionality of DCF itself. I know when we use FPG, it's more accurate. We easily get the result, but for this one, I want to use for multi-parameter, right? So if we use MPG, first is costing is more expensive from this type of fiber, and then for this one, I can do for myself. I can fabricate for myself. If I use FBG, it's hard to me to modify the FBG, and also we don't have the specialties to fabricate the FBG for our in our lab. Yeah.
Yeah, that makes sense. Basically, you can manipulate the fiber much more freely compared to using FBGs,
yes.
Right? Okay. So I hope that answers Intan Fatima Sasila's question. Next is from Ahmed Sabri. You have connected 3 types of fiber to sensing temperature, refractive index, and liquid. So that was the question. Sorry. So 3 types of fiber.
Sorry, again?
So the 3 types of fiber are for temperature, refractive index, and liquid. I think he's asking if each fiber is contributing to one parameter. I hope I'm rephrasing that correctly, Ahmed Sabri. Do you want to clarify for us? Are you there? Okay, let's wait for him to come back. That's it. We have no more questions. Any other questions from the audience? You can unmute yourself and ask away. Any other questions?
Yeah, sure.
Hi, Assalamu alaikum.
Salam.
Sorry, Doctor. I'm meaning by my question, you have connected three types of fiber: single mode and multi-mode and DSP. What's the application that you are using for connecting these three types? By changing the temperature, or put the fibers inside the water bath, or what are you doing in this?
Okay, I use for this one. Okay, I use a single mode fiber, multi mode fiber, and double clad fiber, right? So MMF is function as a speed to speed the light, so that the light can travel through the inner cladding and outer cladding of my fiber optic of my DCF, so that it can possibly sense the temperature reflecting in that, and also discrete water. For discrete water level is because I use a HSMF here, so that the light can travel through the surrounding and then couple back to the DCF. Yeah, is it I'm answer your question? As you can see, the MMF here acts as a coupler. Yeah.
Okay, so I will wait for Ahmed Sabri to come back if he wants to clarify further. But I think the answer was okay. So the next question is from Dr. Muhammad Yusuf Muhammad Noor. Can we apply sensing material on the DCF itself?
Sensing material on DCF?
Mm-hmm.
Such as temperature, right?
No, I say like you coat like a material on the DCF.
Oh, okay. Yeah, we can use that one to enhance the like temperature. We can put something to enhance the sensitivity of our DCF. Yeah.
Okay, so are there any reported works on that, like coating the multi-parameter sensor?
Yeah, it's have. Before this, as I showed you before, there is have people quote the, but for the double cladding fiber, still don't have. But for the single mode fiber or multi mode fiber, there also have a lot people do coating for the type of fiber. Yeah.
Is it the tubing ceramic that you mentioned earlier? Is that the type of coating or?
Tubing ceramic? I don't think so.
Okay.
Yeah.
So we have another question. Thank you, Dr. Musliha. Thank you for the very informative presentation. Can I know, is the response of the temperature sensing fast enough to sense rapid temperature changing environment? This is from Tan Han Yi. Thank you for the question.
How fast it will you want it to be? But for our setup, because we use optical spectral analyzer, right? OSA, so it's depend on our OSA, whether it's maybe we can get maybe in one second, like that, 1 second, and then we can whether how many point we want. So it's depend on our power of OSA. So it really can in real time monitoring, but it's depend on our detector also.
So did you test for the sensitivity of your sensor? Like, that's not the right question. So have you ever tested the performance of how fast your sensor is? Have you ever tested the speed of it?
No. Before this, I don't use for that one. Yeah. So the performance for the fast, how can my sensor? But I can say it can use for real time monitoring. Yeah.
Any other questions from the audience? Very very engaging talk, I think, because a lot of questions coming in. Dr. Tan Hani said thank you.
Welcome. Thank you too for coming today.
So no more questions from the audience. Going once, twice, no? Okay. All right, thank you so much, Dr. Musliha, for the very, very engaging talk. We had a lot of questions coming in, and I think Dr. Musliha managed to answer all of them very eloquently. So we are looking forward for Dr. Musliha to join IEEE Photonics Malaysia for other events.
Yeah.
And I welcome all of you to join
so
us as well. So take care for now. Please join us in our upcoming webinar. I will email you. Don't worry about that. So I'll see you around. Bye-bye, everyone. Take care. Oh, before that, can we have a group photo as like for memory's sake? Can we do that? Dr. Musliha, can you unshare your screen?
Okay. Okay.